Hello, good morning, good evening, good afternoon, everybody, wherever you might be. Well, today we are very happy to have a speaker on site. MARIUSZ TOBOLSKI came here all the way from Wrocław, 360 kilometers, and he will tell us everything and more about locally derived graphs. MARIUSZ, it's all yours. Take it away.
Thank you very much, Piotr. It's always a pleasure to give a talk on the seminar, especially on site. So the talk I'm going to give today is going to be about graphs. It's going to be about locally derived graphs, which is a special construction we came up with Piotr, and I'll mention a reference of the paper. It's something that was like a side project for a bigger paper we have with Piotr. But because it was in this paper that is 50 pages long, you can maybe not even see it or miss it. So here's the talk, so you will not miss it. We're going to be specifically about those locally derived graphs.
It's a local.
It was a very local piece in this paper. So I'm going to start with some motivation, because this talk will be, most of the talk will be about graphs. But the seminar is about C-star algebras or non-linear geometry. So let me start with the motivation. So why do we care about locally derived graphs? I'm going to start with a piece of terminology. So those derived graphs are sometimes called, I have this highlights. So the name derived graphs, sometimes the name skew product is used. So if you, I'm sticking to the original terminology you're going to see in a second, but it's sometimes called skew products. So first, the first motivation comes from understanding group actions on graphs. And here I'm going to review this from the point of view of like the main part of this talk, like the main message of this. The point one will be a theorem that is called Gross-Tucker theorem, that will tell you that if you have a free group action on the graph, then your graph has to be of a very specific form, namely it has to be a derived graph. So the first piece is about group actions. So it's about symmetries. That's the first motivation, and I'm always interested in symmetries, especially in free actions. So that's why I'm interested in this. And then the next thing is that together with Piotr, we define something that is called admissible graph homomorphisms. And we were looking for examples of not necessarily injective, so we're looking for surjective graph homomorphisms. And then derived graphs appeared. And what we did, we were just looking from this perspective, point two, we were looking at derived graphs and we were thinking, how can you generalize this so that still you get this admissible graph homomorphism? I'm going to define this. What do we mean by admissible graph homomorphism in a second? So the motivation is twofold: group actions and morphisms of graphs. And then how those 2 points relate to noncommutative topology or graph C-star algebras is the following. So
I have a question before passing to C-star algebras. There's the notion of graphs of groups.
Yes.
Is this related to this classical subject?
So the short answer is I don't know. I'm not sure. There are some papers that deal with graphs of groups with relation to graph C-star algebras, but I mean, for me, these are just two motivations, and I don't think they're connected to graphs of groups. I don't know. That's a good question. So let me talk about the connection to C-star algebra. So I have motivation coming from group actions. I have motivation coming from admissible graph homomorphisms, and then how do I connect it with C-star algebras? So point one connects via this Comjian path results on cross products of graph C-star algebras. And I'm going to mention this. The result. I'm going to give you the formulation of the result so that you see how group actions and derived graphs are related to cross products. So this, and it's, I think I even mentioned this in the abstract of the talk. And then the second part is that those admissible graph homomorphisms enable you to have contravariant functoriality of graph C-star algebra construction. So, okay, so my point 1 and 2 corresponds to the graph C-star algebra theory as follows. And I'm going to talk much more about point 2 than point 1. But point 1 will also appear. So the motivation comes from group actions and admissible graph homomorphisms. And we're going to look at C-star algebras to those two results. And as I mentioned, this talk is based on a paper in Journal of Development Geometry. It appeared this year, but I think it was, I don't remember when we started this, but a few years back. Right?
We started it ages ago.
Exactly.
Yeah.
But it was published as online first this year. And let's talk about locally derived graphs. So you can find a section in this 50 pages paper.
It's a very long paper.
Yeah.
It's a very long paper, and in fact, let me explain why I coerced MARIUSZ to give this talk, because this is a very long paper, and this is just one section in this paper, and this result, which in itself opens the door to other things, would be lost. I mean, it's we were coerced by referees to give examples. To give more examples, we have to have some new constructions. But then this new construction in itself, as you can see, is worthy a 90-minute talk. So this is why the paper is so long.
Yeah. So let me start the talk. And the first slide, if you talk about graphs, I always have to give you the definition of a graph, but mainly to establish notation, right? So graph is a quadruple where E0 is the set of vertices, E1 is the set of edges, and then I use S and R for source and range map. So it's already here. So S will mean the source map, and R is the range map. And those maps go from the set of edges to the set of vertices. And I think I have a picture here so that we know what we're talking about. If I have an edge E going from V to W, then its source is V, its range is W.
And you should really touch the screen so that
I should touch the screen so that you can see. Yes, exactly. Thank you.
I mean, there is a camera on you, but...
Yep. So that's just the notation. And I will assume that the sets E0 and E1 are countable or even finite. And so a graph is called finite if both E0 and E1 are finite sets.
And if, by the way, we will have in 2 weeks a talk which will deal exactly with uncountable graphs.
Oh, okay.
And the whole taste of the talk will be that we are allowed to take uncountably many edges. Okay? So that's, and it solves Neimark's problem.
Topological graphs?
No.
High cardinality.
Yeah. This is exactly in order to solve, because Neimark's problem is solved for separable Hilbert spaces. But it is still open in full generality for non-separable Hilbert spaces. But if you focus yourself not on arbitrary operator algebras, arbitrary C-star algebras, but just graph C-star algebras, then by taking uncountably many edges, you solve Neimark's problem.
Yeah, it's surely exciting. However, I'm going to talk about countable. Even if for this talk, if you think finite, that's going to be fine for the talk. And many of the results related to group actions on graphs in the book of Gross and Tucker that I'll be relying on for some part of the talk are just for finite graphs. So you can think about finite graphs if you want, but that's not for almost all the results, it's not necessary. Okay, so that's graph, and now a voltage graph. So for this, we need a group. Doesn't have to be finite. We're thinking about discrete groups, and we take a graph. And now there are many. So this is the definition from 1974. There are many names you could use for it. I like the voltage graph. This is the original name used by Gross. You could use base graph, or many other names probably are used. There's a gain graph also, which is so
Twisted graph.
So a voltage graph is a graph, and then you also have a map. And I'm using alpha because that's also the original notation of Gross. So the map goes from edges to the group. So it's like the voltage assignment. So you're thinking about edges getting some labels from a group. Okay, so the name voltage probably comes from things like Kirchhoff's law, and where you assign difference in potentials to different edges of your electric circuit. So that's why I like the name voltage, right? And I'm gonna use it.
Sorry, gamma could be non-abelian.
Oh, yeah.
Yeah, could be non-abelian. Yes.
Just it's discrete. We will need it finite, but
Yeah, I'll also comment on why Gross cared about this particular notion of a voltage. So, and this is my notation, and I couldn't figure out a better one, so I'm going to use it for triple. I need all the information, gamma, alpha. I can just put alpha, but then you forget which gamma I'm using, so then use this notation for a voltage. Example. So let me take the group, and this is on purpose. I have plus and minus, right? So now I can put differences in potential on my graph, and that will be my. So I'm taking a graph. It has vertices V and W, and it has edges F and E. And to E, I'm putting a label or voltage minus, and to F, I'm putting plus.
mm-hmm.
So for E is minus, and for F is plus. And every voltage graph is defined like this. So if you have just a two-element group, you can think of it plus minus. But for this, doesn't have to be an abelian group, doesn't have to be finite group. So there's really a lot of freedom in this definition. So from a voltage graph, you define a derived graph. So it's also known under the name of skew product graphs.
My question.
Going back
Coming back to this voltage graph. So you are not interested in some laws like Kirchhoff laws.
No.
So,
I mean, the one in
But they were.
Yeah, they were interested in that, but also, I mean, one could, in principle, define such laws, right? Or think about them, but I'm not. For this talk, I'm not interested.
but now the voltage is an arbitrary map.
Yes, just arbitrary.
No conditions.
Yes. So this is the name comes from thinking about Kirchhoff's law, but now we treat it as some abstract object where it could be any map, any set theoretic map alpha.
So it's like a label.
Exactly.
Very precisely.
Labeling, but it's just voltage assignment sounds so much cooler. So.
This don't require any other property, like if there exists an inverse edge that you would like.
No.
So this is very general. So it's not because sometimes for the skew product in the skew product literature or in the graph system literature, sometimes people call it cocycle, and then you're thinking also there's some sort of additional assumptions on alpha, but no. So they just call it cocycle, but it's any map.
And see, the reason is that in fact we are only interested not in the edge but in the end.
Yes.
So this is why it's irrelevant.
So okay, if you have a voltage graph, you define a derived graph. As I said, I'm sticking to the original name that was defined by Gross and Tucker. and a follow-up paper to Gross's paper on voltage graphs. And now the definition is as follows, that you define a new graph and its vertex space is just E0 times gamma, and its edge space is defined the same, E1 times gamma. So you're just, suppose your group is finite, then you just multiply as many, you have now as many, if you started with some edge or some vertex V, now you have V labeled by all the possible elements in gamma. And then to have a graph, you also need to have a source map and the range map. And the source map is defined as follows: to a pair EG, you assign a pair S of EG. And the most interesting part of this definition is where we're using actually this map alpha we defined is here to have the range. So the range is, that's this Q product or this twisted part. It's this, we have this twist.
So if alpha is trivial and sends every edge to the neutral element of the group, because we have a trivial Cartesian product.
Yep.
But it's amazing how this little thing, this multiplication, you know, at the end, right? It changes, gives you so many interesting graphs.
But probably they took it like there's the notion of Q product and systems.
Yes.
So
Yeah, of course.
exactly that.
Of course, yes.
I mean, I don't know. So the motivation for Grassi-Tucker is topological graph theory. So they wanted to embed graphs on some surfaces, and they were looking. So this derived graph and the voltage graph, you should think of a covering and the base space of the cover.
Yeah.
So that's what they were interested in. And if you and derived graphs are just nice enough, symmetric enough, because of this group that appears here that you can that they were interested in those.
But by the way, you can see immediately from this definition that it's begging to be used for topological graphs. Because here, if it were not for this thing that we are talking about graphs, not just sets of edges and sets of vertices, because when you look at the sets, these are trivial bundles. Okay?
Yeah.
It's only in the graph that you see this non-triviality. But if you would talk topological graphs, why not to take a gamma principal bundle?
Yeah, exactly. Right.
Yeah.
And that's this our locally derived graph.
Should fit it well. Yeah.
I mean, should fit well, and also because everything is discrete here, right?
Mm-hmm.
So it's very hard to think about things locally. So the only thing we can do is you'll see is to we start with derived graphs, but then we'll try to do something like that, but locally. But we'll get to this in this talk.
Yeah. So it's important that gamma is a group. What about
Okay.
semi-group,
Well, it's
inverse semi-group?
a good question. I don't know.
Well, you need for things to work properly. Basically, what you need to be able to have the inverse.
I mean, yeah, for us,
You have to be able to untwist it somehow.
Yeah, for us it has to be. We'll use the inverse here.
Okay.
To get certain properties for this. But in general, for the definition, it's not needed. But for us, it will be needed that it's a group.
What we really want at the end of the day is a groupoid.
Yes.
Okay. So we need inverses, but
Exactly. So okay. So let me go to an example. So I'm taking the previous example. I'm going to just draw it here. So the example was loop.
the Teplis graph.
The Teplis graph, so it has some edge V. No, it will also delete my loop. So let me start again. So that's my V, that's W, that's F, and that's E. And I have labels minus and plus. Right? And then you can see that now, of course, your edges and vertices, they have to be multiplied. So now I have 4 vertices out of 2 vertices I set it with one with minus, one with plus. And then I have also 4 edges. And Now the sources here, you see there's no twist here, so the sources, edges that started at V, they have to start at the F plus has to start at V plus, F minus has to start at V minus, and the same for, wait a second.
What is a labeling map?
So my labeling map was, oh, that's a good, so my labeling map was alpha of E. There might be a mistake in this picture now. Oh, sure. It's not as easy as it looks to use this. Okay, let's see if it's so for E plus, it should start at V plus.
Yes.
Which is so it's the other way around. So, right, so this should be plus and this should be minus. I don't know how to change this.
No, it's okay.
Let me just do this just for my sake. This should be plus and this should be minus.
Yes, because E minus must start in V minus.
So that's.
But you see, on F, where we have trivial label, this edge is just doubled.
Yeah.
But when you look to a loop, it's not doubled. You don't have two copies of that.
Yeah, so here's the twist. So the twist is in this. So the twist is in this part. Okay, and then of course you can have more and more interesting examples. Okay, so let's go to the next slide. And now I'm going to connect this to the group actions. So the first part of the motivation for this talk are group actions and graphs. So very quickly, let me tell you what I mean by an action of a group on a graph. And here, at some point, I'll have to assume that the group is finite. Okay? But for now, the action, the definition of the action just makes sense for any group. So we say that a group gamma acts on E if it acts both on the vertex space and the edge space. It has to act in such a way that source and range maps are gamma compatible. Yeah. That's the only assumption. And also we say that the action is free if it's free both on the vertex set and the edge set. Right, so this is a very natural definition. And this notion of freeness will be very important in a second. So that's why I'm putting it here. Let me give you an example. I think I have an example, even a class of examples, right? Take any derived graph, and by your action, so here you just multiply on the right by the group, right? And then you have to check that. The only thing you have to check. So this is, well, that's the definition. And you have to check whether source and range maps are equivariant.
Which is obvious.
Which is, well, obvious. And I've written it down just
which is obvious because left and right actions commute.
Yes, exactly. That's the point. The only reason why I spelled this out is that this makes sense only because left and right action commute. So I have to be careful. If I define the derived graph by multiplying on the left, then actions on the right. And of course, depending on your taste, you could define the derived graph by acting on the right, and then your action on the graph will be by multiplication on the left. Right, so that's the key point. So of course, for the source, nothing happens, but for the range, the importance is that the left and right actions compute. Of course, this also means that you could go further and generalize it with bundles, and this is actually we've done it in with the topological version.
When you say we, you mean?
Well, yeah, no, I will say in a second. Yeah, that was the second next sentence. With Lucas Hall and Ben Johnson and Matthew Gillespie, we have the generalized version of derived graphs, but for bundles. But this is work in progress. So. Okay, so that's a class of examples of group actions on, and then we'll be interested in this specific class for this talk. Okay, now a quotient graph. I'm putting a lot of definitions, but also examples, so I'm hoping I'm not boring you to death. So a quotient graph is now defined as follows. It's a very natural definition, right? So we take quotient spaces as my vertex and edge spaces, and now my source and range are defined and also in a natural way, and just I'll emphasize that these definitions, the two formulas here make sense only because source and range are equivariant, right? So there's this natural, the map S and R, they descend to the quotients. Right?
Because of equivariance.
Yeah, because of equivariance. So that's basically it. And let me give you one more example. So here, let's think about this graph and a cyclic action, which just puts, the vertices, which puts the vertices in a cycle.
Cool, that's interesting. How did you do it?
How did I do it? Hopefully, this will help.
Wow. if I wanted to do it, I would have no idea how to do it.
The possibilities
Magic
of this pen are endless. Okay. So I will not. So now we're putting this edge and this vertex here. But so the question is, how the generator of Z3 acts, and it just acts cyclically. Let me maybe write it down. So
you assign just 1 to every edge.
I just
not 0, 1, which is the cyclic generator.
So now the obvious quotient graph is just one vertex and one edge.
Yeah.
So if you think carefully about this, it's again a derived graph, right? If this is a derived graph, if you assign minus, or like the generator of Z3 you assign to this loop, then you get, as your derived graph, you get this.
Yes.
Right? So we already see that there is a connection between actions on graphs and derived graphs. And now in the next slide, I'm going to not in the next slide. Okay. So there will be an intermission. So, so that story was about derived graphs so far, and about actions. So that was point 1 of my motivation. So those group actions. And now point 2 was about morphisms. And I want to talk about morphisms a little bit, specifically that I want to know what is a graph isomorphism, which is a natural notion, but let me just make sure we're on the same page. So, yep.
Back to the slide. So now we are talking about quotient graphs for arbitrary actions.
For arbitrary actions,
yes. Yeah. But what about if this acted graph by group, if this is the right graph?
Exactly, yes. So
what can be said about this quotient?
So it's exactly a voltage graph started with.
The same you started with.
Yeah. Yes. Okay. And it's going to be on the next slide or just after, but it's a very good question.
Because of freeness.
Yeah, exactly. That's it. So I'm just
trivial bundles.
Yeah. Because of freeness, it will work. So let's see. So first of all, graph homomorphism. So by graph homomorphism, so I have a phi will be defined as a pair of maps. So I have a map between vertices, I have a map between edges, and they have to satisfy the two relations here. So they have to preserve the structure that I have, right? So the source and the range map, they have to intertwine the source and the range map. And an isomorphism, as you can probably guess, is that when phi 0 and phi 1 are bijection. Any questions? No. Okay. So that's the notion of a graph homomorphism and a graph isomorphism. And I maybe need this slide because I will say that two graphs are isomorphic in a second. So I wanted to to have this. And a class of examples of graph homomorphisms will be again coming from derived graphs. So if I start with and that's basically why Gross and Tucker were interested in those, because you have some sort of a covering. So if I have a derived graph coming from a voltage graph, I can define the following map. The natural projections, right? So my vertex space was E0 times gamma. I'm just projecting on the E0 component, and here I'm projecting on the E1 component.
Which is like taking the quotient.
Exactly, which is like, which is exactly like taking this quotient we talked about, right? Because we're just by acting on the right, you're making this part disappear, right? Because the action is free by this multiplication. Okay, so this covering projections, you can check that this is actually a homomorphism. So you can check that pi 0 and pi 1 satisfy this. It's not too difficult because on the right component here, we're forgetting about the twist when we're projecting. So there's not much. So that's a nice class of examples of graph homomorphisms. And we were looking at this class with Piotr. That was our starting point here, and I'll go back to this in a second, but let me now tell you about two results related. One is the one Tomek already asked about, and the other one is the Gross-Tucker theorem, which I think is very interesting from the point of view of how to connect derived graphs and the group actions on graphs. So first of all is this proposition that we already discussed, that if I start with a derived graph, coming from a voltage graph E gamma alpha, then the quotient graph for the natural action, right? So the action on the right is isomorphic to E. And this is more or less straightforward, right, to prove this. So this is not like the big interesting result, even though this, but what is interesting is that, and I don't know if I mentioned this already, is that this action we discussed, oh, sorry for that. Go back here. That I didn't emphasize that this action was free, right? But it's obviously it is a free action because multiplying on the right is a free action in a group. So what is interesting now is to ask what other what classes of graphs are exactly derived graphs. So which graphs look like derived graphs? And the answer is, the Gross-Tucker theorem is that whenever you have a free action on the graph, it is a derived graph. It is isomorphic to a derived graph. Let me state now the theorem. Sorry. So the theorem is, and here, so okay, I think they stated for finite graphs and finite groups, but I'm pretty sure it's not necessary here. But let me state for finite groups and finite graphs. At least in the book, at the very beginning of the book, they say, oh, that's the book I'm talking about, topological graph theory. That's where you can find the proof. And in this book, in the introduction, they say that unless explicitly stated, everything is considered finite groups and graphs. So if I have now to the theorem, if I have a graph, a group acting freely on a finite graph F, then first of all, there is a voltage assignment from the, and here there should be one, right? So from the edges of the quotient graph by this action. So I have a free action. I can define what is the quotient graph, and there exists some labeling and an isomorphism such that F is actually the derived graph for this label.
Equivalent. Yeah.
Equivalent. Yes. So if you have, so any topological graph with a free action is isomorphic to a derived graph.
Wait, you said topological graph?
I said topological, sorry. Yeah, any graph, any finite graph. Sorry, yeah, of course. And that's very interesting because if you have a free action on a finite set, then it gives you automatically a trivial bundle. Right? Always, and because of the fact that everything is discrete. So a free action on a finite set has to give you a trivial bundle. It's very easy to write down what it is. But so that's basically my understanding of this theorem, is that free actions, when everything is discrete, lead to trivial bundles. And derived graphs are kind of a version of a trivial bundle. Right? And now, if you would like to think about topological graphs or topological quivers, I can very easily find examples, and this is in the work in progress with Lucas Hall and Ben Jones and Matthew Gillespie, that we give you examples of things in the topological realm where Gross-Tucker theorem is not. Okay, so this is a very theorem that is true only for finite graphs or discrete graphs. And
Is it really so difficult to prove?
no, I'm not saying that. I'm calling it the theorem in the book. If you and because in the book it's called the theorem, and I mean the proof is. I don't want to say straightforward. It's if you see the proof, maybe coming up with the proof, it's not as easy. But the proof is. I mean, it's still a page of reasoning,
okay.
but
If it's a page, okay.
yeah. Okay. So.
I have a comment.
Yeah.
So you are insisting on this discreteness,
Yes.
and you are, of course, interested in this topological version.
Yes.
There are analogical results in algebraic topology when you have bundles which are not trivial, which are defined in terms of twisting cocycle.
Yes.
Okay, and then very similar phenomena like this cancellation of so free action is more important than finiteness.
Yes.
And and this reconstruction of this free action is a reconstruction of a bundle structure.
Yes.
In terms of this twisting cocycle.
Yes.
So I see
that's true.
this theorem is
So that's why people call this a cocycle sometimes. It's not, right? Yeah. So there's surely that's a good analogy. Okay, but so this is theorem just about graphs. So so that's the first part of the talk where I'm saying okay, so that's why derived graphs are important, because if you have any free action on the graph, then it is isomorphic to it. So that's the motivation for studying derived graphs. And then, of course, you can think of generalizing the Gross-Tucker theorem. For example, I'm now trying to generalize this with Björn Schaefer. We're trying to generalize this to quantum graphs. Right? So you can ask, is Gross-Tucker theorem, or what would it mean to have a Gross-Tucker theorem for quantum graphs, and stuff like that. So this is very interesting, exciting result. And now I'm going to talk about point 2. So now why, in the table of Piotr, why we were interested in derived graphs. So I'm going to first review what is admissible in the context of graph homomorphisms. So first, let me remind you that the vertex V is called regular if the following condition holds. So it's not a sinc, and it's not an infinite emitter, right? So it emits only finitely many edges, non-zero finitely many. And edges that only emit infinitely many, vertices that emit infinitely many edges are called infinite emitters, and this part, so edges that don't vertices that don't emit edges are called sinks. So we're interested in regular vertices. So only things that emit finitely many edges. And now a graph homomorphism is called admissible if it satisfies 3 properties. So first of all, it has to be proper. And by proper, I mean that the maps phi0 and phi1 are finite to 1. Right? So preimages of every point is preimage of every point is finite. It's a finite set. And this properness, so already here, let me mention that here, finiteness of a group will be important to get. So we'll be thinking about this map So you can think about, when I'm talking about this homomorphisms, you can think about this pipe that goes from a derived graph, the voltage graph, right? And because here we have something like EI times gamma going to E I. Right? If gamma is not finite, then properness will immediately fail. So I'm actually going to give a proof of this fact that this map is admissible in a second. Let me first finish what admissible.
Sorry, could you remind me, in the context of Katsura's topological quivers, does properness
Yes.
means topological properness?
Yes, exactly. Yes, thank you very much. I forgot, because so this is the definition we came up with Piotr a few years ago, but we were not aware that already Katsura already defined this. He called it regular factor maps in this paper on topological graphs, where proper meant exactly properness for locally compact spaces. So primitives of compact sets being proper. Yes, that's a very good question. So now properness is the first point, and then the second condition is something that we call range bijectivity or target bijectivity. And I've written it here in the way that Katsura writes it in his paper. So the condition is as follows: for every edge in the codomain, right, of the map. So for every edge and every vertex now in the domain, such that, and here this relation is important, if I find any pair like that, then there exists a unique edge in the domain such that the image of this edge is F and the range is V. Right, so this is the range bijectivity. You can write it down in the various ways. One way that, well, I like is to say that, so I have my, so I have my map phi 1 going from here, and then I have my map phi 0, and then I have my range.
Range, that's
the full point.
That's the whole point, yes. And then I have a range in F, and then I have range in E. And being a graph homomorphism means that this diagram is commutative. So range bijectivity means that it's a pullback. That's exactly so.
This is what we discussed in Florianopolis.
So graph homomorphism.
And you insisted that it must be source.
Must be so.
So graph homomorphism means that we have commutative diagram, but then range bijectivity means that it's a pullback.
If and only.
Yeah.
That's it and only if.
That's it.
Yeah, that's
Well, here not quite, because for graph homomorphism we have to have the same diagram for the source. But,
okay. Yeah. So the range part, the range part of the graph homomorphism. Yeah. Yeah. Thanks.
but here it's really if and only.
Yeah. For the range bijectivity, it's really if and only if. That's something that I find really satisfying, and so it's because this means that this condition is very natural. Right, so it's you have a commutative diagram and you ask if it's a pullback or not.
If I might throw in a quick comment, when with Francesco and Gilles were working on the relation morphisms, very strangely it turned out that actually this range or target subjectivity is quite important at a deeper level. And later on you need also injectivity. But But we discovered that if we want to talk about the relations even between path algebras, let alone Levitt or sister algebras, we already need to have target surjectivity. And surjectivity, well, it's obvious what is meant, because when you have a commutative diagram, of course, you have a canonical morphism into the pullback.
Yes.
And you just want this to be an isomorphism. So in particular, you want it to be by surjective and injective. So surjectivity somehow is more important of this canonical map.
Okay, so let me I'll comment that I came up with this idea of having a pullback here by looking at the paper of Quigg,
Yeah.
Kumjian, and So and they were looking at bundles. And if you have like two bundles, right, and morphism between bundles, if this map is equivariant, then you always have a pullback, right? You can pull back the bundle here. Well, you have to look at it differently, but you can pull back this bundle data to this one.
Mariusz, I'm a bit concerned. You just used half of your time and did 10 pages out of 78, which means you should talk 5 or more hours.
21.
Yeah.
Ah, okay, 10 of 21. Okay, so what is this here, 10 of 78?
Count with all the transitions, whenever.
Pause it.
Okay, pause it. But still, it's 10 out of 78.
Yeah, because it's broken.
The counter is broken.
Yeah, the counter on the left only changes whenever the whole slide changes. The absolute amount on the right is counting all the
Okay,
transitions.
thank you very much.
Yes, so I don't have five numbers.
Okay, okay. No, so we are perfect. You're on the spot. You know.
Especially the last slide is thank you.
Yeah.
Okay, let's maybe still go a little bit faster. So regularity just means that preimages of regular vertices are regular. So if I take a preimage of any regular vertices, all the vertices in the preimage has to be regular. So that's regularity. And instead of giving you an example, I'm going to give a proof for this map that I just erased, this covering projection, where I'll prove those three conditions. And so recall we have this projection, and now we want to prove it's admissible. And here I'm going to really need that gamma spike.
Properties.
And that's as Bill said. So I needed gamma finite to get properties. So without gamma finite, I don't have admissibility, and properness is really important for this. Now, okay, so to prove target this range bijectivity.
And here need the inverse in the group.
Yeah, here exactly. Here's the inverse. So now my codomain is here, right? So I'm looking at any edge here. So I'm taking edge in E and a vertex in the derived graph, such that the range of E equals to pi 0 of this. But now pi 0 of this is just V, right? And I need a unique edge such that this is satisfied, that pi 1 of this edge is E, and that range of this edge is VG. So let's see. So you can just guess by looking at this that this will be the edge unique. Mm-hmm. And it will be unique by the uniqueness of inverse, and it satisfies the two formulas because, well, first of all, this one is easy, right? You just project it onto E. And then the other formula is true by how the range was defined. So the range now multiplies by alpha E inverse, you get. And here you get the range of E, which we already know is this. Right, so that's how you prove range bijectivity. And now regularity is also goes the same way. I mean, you just follow the definition and then it works. You take any regular.
But here you use finiteness of a group again. No,
that's
well. Well, I mean,
so first, so I'm taking any regular vertex in the V, right? That's pre-image are all the VGs, and I'm saying exactly. Like, so take any G. Then I want to prove that it's not a sink, that it's not an infinite emitter. first of all, I know because V is regular, there exists some E such that, well, the source of E is
How do you go like from the fact that the agreement of V is finite, that the agreements become a G or G?
That's a good, yeah.
Yeah, but there is
You're right.
finiteness of
You're right.
gamma.
You're right. Thank you. Thank you. That's true. So here, to prove this, I need finiteness of gamma again.
Yeah.
Yes.
Because any edge of the form EG, where G is anything from the group.
Yeah. Thanks. So yeah. So that's a slide that was, I want to review admissible graph homomorphisms, but they appeared at this seminar so many times already that I wanted to make it in some in this way, just by giving you this proof. So okay, so with Piotr, we're interested in those admissible homomorphisms, and now I think I'll tell you why, right? Because we want to talk about graph system algebras. So this is again just to establish notation, the standard definition of graph C-star algebra. So you have a universal C-star algebra generated by mutually orthogonal projections that are labeled by vertices, and then partial isometries labeled by edges. Oh, here should be one. But we're assuming, because I'm not saying anything about the graph, if it's finite, I'm just assuming it's countable. So I also need mutually orthogonal ranges. And then I have three conditions called the Konstriger conditions. And I'm using the convention with range here, right? So there are different conventions. So that's the one. So the first condition is that it tells you what happens if I take S star S, then you get this projection. And for S star, I have I have a different formula, but only for regular V. That's very important. So not for sinks, for infinimeters, this formula does not hold. However, for all edges, this formula has to hold. And that's, you can prove that this is a compact set of relations that define universal C-star. And now, what we proved with Piotr, but also then we found out later that Katsura proved it already, is that if you take an admissible graph homomorphism, then those two assignments, I'm giving you here, so I'm taking all V's in the pre-image of a W. So I take I want to have a homomorphism. To have a homomorphism from a universal C-star algebra, it's enough to just say what it does to the generators. So I'm taking the generators PW, where now this is in C-star F. So it reverses the arrow. Right? So I'm going from E to F, and now my homomorphism goes from C star F to C star E, so it will be a contravariant functor, or like a contravariant assignment. So now those two formulas.
So now I can see why you need properness.
Exactly. This is also where you see why you need properness. And so I have many kind of arguments in favor of those two formulas. So first of all, if you just look at the very general case, and this is something that Piotr taught me, is that if you just look at path algebras, or even before path algebras, you can define some sort of, to any graph, you can define some sort of like a semi-ring.
Yeah.
And then very natural way of dealing with homomorphism of graphs is taking pre-images, right? So here we're looking at pre-images. That's where the contravariance comes from, and that's why this formula is the right formula. Also, if you look at the version of graph C-star algebras coming from correspondences, you see that correspondences of graphs are correspondences over commutative C-star algebras over the vertex space. And then these formulas are exactly the ones that give you the Gelfand-Naimark duality on the coefficient algebras of those correspondences. So there are many arguments for these formulas to be the one, right, to look at for the right contravariance. So what we did is that we knew that we wanted those formulas, and now the question is what kind of morphisms of graphs will give you a star homomorphism when you define those formulas. So what you have to check are those three relations, right? 1, 2, and 3. And it happens that 3 is kind of automatic.
Well, because it comes from path
Yeah,
algebra.
the path comes from path algebra already.
So just properness takes care.
Yeah.
So could you remind me? Of course, this part with projections
Yes.
is obvious. It must be so. Okay. But how do you apply this 1, 2, 3 to prove that this is a good formula for the star homomorphism? On the level of
You just check it, but under certain
No,
conditions.
but how do you use this 1, 2, and 3?
Oh, so no, so it's the other way around. So we are saying this is the right formula,
And now we find
and
conditions.
now we find conditions on graphs such that 1, 2, and 3 are satisfied. So it's not the other way around. It's not that 1, 2, and 3 and the formula, and then the other
But
argument.
you claim that it is a good idea.
Yeah, so that's what I claim. Yes. No. I mean, I was trying to argue why this is the right formula. I have a lot of examples. Like, first of all, all of this comes from the case that was already well known, where there's no pre-image when the map is injected. Right? And then you want to have a subgraph, and you want the things in the subgraph to not change, to be the things.
So if the graph is discrete,
Yes.
no edges,
Yes.
that this is the
This
typical
is the
formula
Yes.
for functions of finite.
Yeah, this is just a pullback.
Exactly.
Yeah.
And then you're asking why this?
Yes.
Yes, exactly. So one way of seeing this is
Because
that
pullback is on the space of paths, not just the space of vertices.
we're actually looking at space of paths.
This path algebra is just finitely supported maps from the space of finite paths into your field. So if you just pull back this algebra,
But this formula is only about edges.
yeah, but if you have about edges, you have about paths.
Yes.
Yeah.
So we want to have the same formula for paths.
Mm.
So if you think about vertices as paths of length 0 and edges of paths of length 1, then this is what you get. So the general formula will be about paths, and this is the special case.
You see, here, because a graph homomorphism preserves the length of paths, you could write just one formula where instead of W or F, you just write a path.
So it extends.
It extends. Here's no problem.
Exactly. And what we also
But only because we preserve the length.
Yes, so exactly what Piotr said is that because you preserve the length, we want this to be gauge equivalent. I'm not going to tell you what the gauge equivalent means in this talk. It's not that important for the talk, but it's important for this theorem, right? That here we have the same kind of projections go to projections, and those partial isometries go to partial isometries. Again, maybe a sum, right, of partial isometries, sum of projections. So we're in the same kind of grading component. So this is another argument why this formula is the right one. But
But in general, if you have partial isometries,
yes,
even if the ranges are orthogonal, mutual orthogonal, is it true that if you have a finite sum of such partial isometries, the result must be a partial isometry?
Yes. Because
It is
because of orthogonality, yes.
Okay.
So like some orthogonal projections is a projection.
Right?
exactly. So now, as you can imagine, so the unique properness of your admissible morphism.
Yes, so they're mutual orthogonal, they commute. No?
Yes,
Yeah.
you need the mutual orthogonality.
Yeah, that's what I said.
You said that.
That's what I said. Okay, great. So now let me only tell you an idea of the proof. Where do you need the admissibility conditions? So properness is needed just even to write down the form. Otherwise, those formula would not make sense. Now, range bijectivity is needed for 1, and regularity is needed for 2. And it's very easy to hear regularity. It's in the name.
And you see, this is why I so much dislike writing the definition of graph sister algebra like this. Because, in fact, you don't have just one as you wrote it, but you have 1 plus orthogonality of ranges.
Oh yeah, but I wrote.
I know, but then we point at one and you say, aha, so this is for what we need target bijectivity. But target bijectivity does two things. It does one and neutral orthogonal ranges. I don't understand why not to write Kroneker's delta and E and F and have a Dillard package.
I guess it's just a question of taste. Yeah, but you're right. If mathematically, I'm this and this.
That's what is taken care of by target bijectivity, and that's what I call the Kurzkunstkrieger relation.
Exactly. And then 2 is taken care of by regularity. Okay,
Correct.
so that's and we were interested in this theorem, and we were interested in admissible graphs. So let me maybe tell you that people already knew a lot of this in the graph system algebra literature when phi is injective. Because if phi is injective, then I have this proposition that you can prove that if you have an admissible graph homomorphism, if phi is injective, then two star homomorphism is surjective. So if you're talking about point 1, you're talking about ideals. And if I sneak this information about gauge equivariance, so now we're talking about gauge invariant ideals.
Yeah, which are classified.
And these are classified, okay, by, complements of subgraphs. Just subsets of the vertex sets. So now, if you know all injective admissible graph homomorphisms, and if it's injective, then we're thinking about graphs. So I'm going to say, if you know all admissible subgraphs, you know all gauge invariant ideals. And this was already classified. What we were interested in, Piotr, is when this is surjective, and this was not explored. So we wanted to find a lot of examples, new examples of surjective maps, and then the derived graphs came as one of the examples, and we were thinking, how can you generalize this so that you're not losing admissibility, but somehow this derived graph construction is more general. But before I go to this, I want to mention this congruent path result. I'm not going to talk much about this, but I wanted to show you the results so that you see that this is the derived graphs appeared already in the graph system algebraic literature in this result. So of course, what we know is that because this pi is surjective and we showed that it's admissible, so now we have an injective map of this sister algebra into this sister algebra. So this is a subalgebra, but what kind of subalgebra? Turns out this guy can be thought of as cross product of this algebra with a certain action. Okay, so it's not any subalgebra, it's a subalgebra given by the cross product construction. So if you start with voltage graph,
So could you go back to the previous slide just for a second?
Yeah.
Just
this one?
No.
Oh, here, sorry.
Yeah. Just a quick comment, but you should not think about it like, compare Hausdorff spaces and pullbacks of continuous maps, because it is true that if phi is injective and phi star is surjective, but it is not true that if phi star is surjective and phi is injective.
Yes. And now we'll have an example.
It's such a break, so you can check it.
Yeah, but I mean, you have counterexample.
But let me maybe mention that at this point 2, to prove it, we used gauge invariant uniqueness theorem because it's about injectivity.
Yes.
So it's, but of course you can probably check it.
No, I'm talking about because in the category of comparable spaces and unital sister algebras, both statements are if and only if.
Yes, exactly. Here we only have, this is only one way. Yes, because I'll give you an example of a surjective map at the level of graphs that will give you isomorphism at the level of C structures. Yeah, that's a nice comment and something to have in mind. So going back to this theorem, so now for the statement of the theorem we use abelian, right? And then we say if you have you take a voltage
not necessarily
graph,
finite.
Yes, not necessarily. If you have a voltage graph, so from this data you can define an action of the dual group such that the cross product by this action by the dual group is isomorphic to the C-star algebra of the derived graph. So this cross product is again a graph C-star algebra, and the graph it's based on is the derived graph coming from E.
So gamma hat is really the Pontryagin dual? So
yes, gamma hat is the Pontryagin.
It's a compact group.
Yes. Well,
gamma is discrete,
I'm
right?
thinking about discrete. Yes. So
gamma hat
discrete
should be
abelian.
compact.
Yes, so we should be finite. Even.
So what is the relation between gamma and alpha?
So that's a good question. And you just using alpha, you define gamma. It's much easier to see it if you think about this in terms of coefficients. So this result was generalized by Kaliszewski, Quigg, and Rayburn. And when you think about coactions, it's like this alpha is an element in the group, right? So you can think about the group Caesar algebra. That's your dual group. That's your quantum dual group. And then the coaction is just to the edge, to this, I think this is correct. So to a given edge, SE, you put this. I'm not entirely sure, but I would guess that would be your formula for the coaction. Or lambda is not generate current. Right, so that's how you use alpha to define this. And then I don't remember exactly how to define this gamma having alpha, but it's in their paper they have the formula for gamma. So maybe I should have added this to the slide. I don't remember the formula for gamma, but it's something like this. Mm-hmm. Right. So this is a very interesting result, which tells you again that derived graphs are interesting, and you can think of them. So this is the whole talk is just like one big commercial for derived graphs. So that now when I will start talking about locally derived graphs, you'll be like, okay, yes, so he's generalizing something that's interesting.
Okay.
So let me go to locally derived graphs.
So now we begin your talk.
Yes, now I really begin my talk. And this construction is not that straightforward. So there's a lot of moving pieces, and let me go very thoroughly through this. So now I want to define derived graphs, and I want to do it in such a way that that it's still some sort of a covering, that I have a map from the thing that I constructed to the graph I start with. I have some graph E I start with, and this map has to be admissible. So I wanted to generalize derived graphs in a way that I'm still having an admissible surjective graph homomorphism. So the first part of the data is I need a pairwise disjoint family of subgraphs. Right, so I'm not assuming E is finite, so it could be I have any graph, but I have a distinguished family of pairwise disjoint subgraphs, and for each subgraph, I have a group. Okay, so I have a family of groups, I have a family of subgraphs.
For the time being, they are arbitrary groups.
Later on, they will become finite again, but for now, for the construction, it's not necessary to have finite groups.
But the beauty is that we can have infinitely many of these finite groups, and their size can escape to.
And now the first subtlety is that you're thinking, okay, I have those graphs, and then I have groups. So let's do derived graphs for them. So the labeling should be of edges in the subgraph.
And it's wrong.
And it's wrong, right? So because we want to go even more like something more general. So we're looking at all edges that end in the subgraphs. Okay. So of course the edges in the subgraph will be part of this, but there are some edges that end in those subgraphs, but are not necessarily part of the subgraph. Yeah. And we label those. So this is our voltage assignment we assign to those sets.
Well, they're still disjoint sets.
Still disjoint sets.
But if this family is one element family,
yes.
Yeah, no problem.
then you have a different voltage assignment than in.
Well, I mean, it can be a subgraph. If it's one element, it could be a subgraph. And in fact,
I will give you
first interesting example was just a subgraph.
Yeah, exactly. That's true. So the thing will be that the whole idea of this construction is that some pieces of the graphs will be not touched at all. So there will be just some, and then the subgraphs I have will be kind of derived, but it will be something more because we will also like unfold everything that was ending in those subgraphs. It has to also unfold.
So it's a two-step generalization.
Yes.
First, the number of cardinality of the family, and second, allowing the subgraphs instead of the total graph.
Precisely.
Yes.
And you should not think about this family as a covering of a graph. It is not.
No,
It might be, but
it might be just one subgraph, and then we have some part that will not be
It will be a covering of a subgraph.
Yes.
yeah.
Yes. It's covering of some.
It's just a bunch of theoretically joint subgraphs. Of course, they can be partition of a graph, but they need not.
And then I'm going to need this notation. So I'm sorry. So then the definition we have will be the whole slide. So I need to use as much notation as possible. So this curly E1 will mean this union, right? So I'm taking all of those sets here for alphas, and I define a map, big alpha, no, alpha without any subscript I, and it lands here, and my curly G
Is a groupoid.
Is it? Yes, exactly. I mean, it's a family of this
Bundle of groups.
It's a bundle of groups.
Which is a very special.
Very special groupoid. I'm going to mention something about groupoids at the very end, because for now it's not that important that I have a groupoid. I mean, it happens to be because we just took a family of groups. So and please try to remember this notation. I know it's going to be a lot because I'm going to introduce more notation. First of all, I'm calling this triple a locally voltage group. So I have this local data. So I'm not labeling, I'm not assigning voltages to the whole graph. I'm only locally to those subgraphs and things that end in those subgraphs. I'm giving them labels. And the labels are in different subgraphs. There are different groups, right? So there's this is a very fast generalization of the derived graph. Okay, and now I'm gonna need some more notation. So because this was E1, so that was like my edges. So E0 will be the sum of all vertices in all of my subgraphs. And then I'm also going to use E times G to be this family. So I'm taking now products here and products here. So you already see that for derived graphs, edges and vertices were kind of multiplied by as many elements as the group had, and it's happening the same. So now the idea. So the idea of constructing this locally derived graph is that in this locally voltage graph, we replace every subgraph EI by the derived graph. But then also we unfold every edge that does not belong to any of the subgraphs but ends in the subgraph. Yeah. And I'm going to give you examples, so don't worry, because also one thing is that it would be very nice to have more examples. And so if you're interested in this, you can try and find some more interesting examples.
So, Marek, but I don't like this notation because Cartesian product has its meaning. When I take the set of Cartesian product of sets, it has its meaning, and now we gave it a new meaning.
So maybe I should use a different symbol.
Different symbol,
Yes.
Like E0 subscript gamma.
Yeah. You're right.
Maybe
You're
fiber product of
Fiber
I.
product, exactly. A fiber product over I. You're right. Tom.
Great.
This is a fiber product over I.
So just for notation.
But maybe not, because I have a question. So the domain of your alpha uses this union.
Yes.
On the right-hand side of the codomain, you have the disjoint union.
But both are disjoint, right? All these ranges are disjoint.
I just
Are these ranges
yeah.
are disjoint?
Yeah, it's always. If graphs are disjoint, then the ranges are disjoint. I mean, pre-image of disjoint sets are disjoint.
because the-
Yes,
Okay.
exactly. Yeah, so that's maybe not.
But it's again a confusing way of writing.
Yes, but I think it
You allow something which can
already in I think also in the paper we wrote like this, so that's because but it's so okay. So I know it's a confusing way of writing it, but believe me, the next slide you will understand that I need notation. So that's the definition. Right, so first I'm looking at vertices of my locally derived graph. I'm taking all the vertices in E without the vertices in all the subgraphs. So and this is not doubled. This is just copy. I just copy this part. I'm doing nothing with this part. But whenever I have something in the subgraph, it's multiplied by those elements. So this is this sum of maybe. So this part is the sum of E0 times gamma I.
So it's like a high scraper above E0.
Yes, exactly. Exactly. Yeah.
And the same you do for E1. Right? So first you take all the edges in E, and then you remove all the edges that were in the subgraphs and ended in those subgraphs. Right? So you just say, it's easier to say that you just remove all the edges that ended in the subgraphs.
But sorry, if I might continue this analogy, because I kind of like it. You can think about a city, and you can think about the ground area, and then you can have a bunch of independently owned squares, okay? So they cannot intersect because they have different owners. And then you build skyscrapers. But the thing is that in this case, we also have some staircases going into the skyscrapers, which start beyond the place on which the skyscraper is built. So you should think about it as this, city full of skyscrapers, but with some additional, scaffoldings or stairways that go to the skyscrapers to different floors, but they start beyond the ground from which skyscrapers goes about.
Yes, exactly. So you can think about capitalism, you promote it in your class. So you go through those letters. So anyway,
Just please don't explain this formula.
Yeah, so the formula is,
It's just bookkeeping. It's completely
it is
trivial.
bookkeeping. So what we're doing is that if something, so let me just very quickly, something started outside, so here, if something started outside of subgraphs, then we're just saying if this edge did not end in a subgraph, then nothing happens to it. So it started where it started in this piece of the graph we started. But if it didn't end in the subgraphs and also didn't start in the subgraph, then you do nothing with it. But if it started in the subgraph, then, well, you put it here in this part where 1i is the neutral element of your gamma I.
Let me put it this way. The only interesting case, which is non-obvious, and this was your brilliant idea, Mariusz, is the following, and we needed it, otherwise admissibility would be false, is that when you have a case when your edge ends in a subgraph, but does not belong to the subgraph, then the way you unfold it, that you keep its beginning wherever it is, and then you unfold it to different ends.
Yeah.
But you keep the beginning. So then you have like one vertex, and you have these many edges which go to all these different unfoldings. So this is a different way of unfolding that you have for edges which are in the subgraph, because then you unfold the same way the beginnings as you unfold the ends.
So let me go back to this.
This is the scaffolding. Exactly. But I said it's slightly confusing because I can imagine that I have an edge which begins and ends in a given subgraph, right? But does not belong to the subgraph.
Yes. That's true. But as Piotr said, so this is just bookkeeping, and the idea is that you just have, just as it's here. So for any subgraph, you build a derived graph from it, but then if something ended there, you have to unfold it.
Yes.
And you have to keep track where the vertices went, and you have to make sure that.
I see how nicely non-trivial examples.
Exactly. So let me start with some examples. I have two examples that I will just discuss in detail. So first take a graph R, which is, well, happens to be the graph of the Kunz algebra of 2. So you have just one vertex and two edges, two loops actually, because source and the range of E is V and the same for F. So source and range is V. So you have, so the graph, I don't know why I didn't, probably I didn't have enough space, but it's just this graph. You have two. So this is the graph the graph system algebra of this graph gives you the famous consumption O2. And now we to have this locally derived graph, we need a family of subgraphs, but we'll just take one subgraph.
But really a subgraph.
Yeah, but really a subgraph. So I call it E, and you have well, the vertex is the same, but we take just one of the loops, right? Just one of them. And the other one is fixed and we do nothing. So, but however, if you look at the range, the inverse of the range of V, well, then you need to put labels on both of the edges. And for the choice, if for E we get minus and for F we get plus, we have the following graph. And hopefully this time there's no mix-up. So first of all, we're looking at vertices, right? So we only the vertex of a subgraph is also the vertex of a graph. So we double this one. Because you remember that if you had vertices that are in the subgraphs but are not in the bigger graph, you do nothing with them. But here we don't have vertices like that. So we only have one vertex and you double it. And then you have to double all the edges here. However, it's done in a way that, well, I don't know if it's seen, but this, if you see this, like this guy goes here, this -1 also goes here, the F minus, and then this one.
Okay, so now if you look at it the following way, look what happens to E. That's the usual derived graph construction. Out of one loop, we get a composed loop, okay,
Yes.
of length 2. That's how it was before with this triangle and so on. But now here you can see the effect, which is very interesting for us and gives us some interesting new graph sister algebras. Namely F, you see, F is beyond the subgraph, but it ends in the subgraph.
Yes.
So you have this unfolding. You always begin at one vertex, V plus, but once you end in V plus and once you end in V minus. That's this unfolding I was talking about. And it gives you a completely different graph than you would get if you would apply this derived graph to the whole Hawaiian graph.
Yeah, even the same labeling.
Even the same labeling.
With the same labeling, you get a different graph.
Different graph. And somehow this graph turned out to be very exciting because we happened to be in Arizona with Jack Spielberg when working on this, and Jack immediately jumped and said, wait a second, these are 2x2 matrices over all three.
Yes, exactly. So if you can look at this graph, you can compute the K-theory. If you look at Rondon's classification theorem, then you can obtain that this is actually 2x2 matrices over all three.
Well, just in classification,
Yeah, just
how can
because-
you say that the same two?
Because if you know K groups and you
Yeah.
have a class of one, you know, and the class of one is,
so you can keep that.
yeah. So
Otherwise, just from the K theory, you wouldn't see that.
Sure.
Yeah, exactly.
That's the morita, but when you know the class of one, you have, yeah.
Just for K-theory, right? You don't know. So that's why I said K-theory plus this classification result, which basically does what
You
does
need
that.
the class of
Yeah.
one in case.
Yeah.
There's no way to see this in terms of graphs
There is.
without classification.
There is.
There is.
Yeah. That's my work with young you.
Oh,
I have a bit of a weird question because from what I understood, the deal breaker here was the inclusion of F minus. because, as you said before, if not for this unfolding of this edge, the admissibility would break. But does this graph without this F minus also have any?
But what do you mean without that mind?
So you're asking about
What I mean is that what I mean is that when you've introduced the definition of this partially derived graph, you made a big deal of the thing that we have to unfold the edges.
Yes.
That
oh, that's true. So
and I wanted to ask what happens in this example when you don't do that.
Well, in an example, nothing happens, but then you see, just like we have a natural collapse of the derived graph into the base graph or voltage graph, we also have a natural collapse of a locally derived graph onto the base graph. And we want this collapse to be admissible.
Okay.
And without this additional this time print, okay, which MARIUSZ beautifully discovered, it wouldn't be admissible.
Okay.
So it wouldn't use a star homomorphism of graph system.
yes, that's so maybe it was. I should give you this result first, but so I thought that first I'll give you examples, and then I'm gonna talk about where it would break if you want to now have
You really cannot write down the isomorphism.
isomorphism.
What isomorphism?
Between M2 of O3, I think, yeah, there's a formula because you have a...
No, we have the formula. This is my work with young people. We have.
we can.
Okay, so you don't need to go to classification.
No, but it's, we are sort of describing it historically. We are the Blackboard in Arizona and Jackson. Wait a second, by classification, I know what it is. Because at the beginning, we had no clue what it was.
Okay.
Yeah, but that's a very good point, actually, that maybe in the new version of slides, I should write down there's a formula for the isomorphism, because that's how I describe it historically, you're right, because this is what happened, this is how we first proved it. But then, of course, when you know it's true, then you can find a nicer way, an easier way. Of course, there's a specific isomorphism.
There is a certain absolutely natural graph whose graph system algebra is Mn of Om, or any numbers n and n. And then from this kind of a graph, you can construct a path homomorphism of graphs into something like this. But this path homomorphism of graphs induces an isomorphism. And this way you can have
The path homomorphism.
Well, he didn't speak about it here, but there's a more general concept of a homomorphism of graphs which does not preserve the length, which means you can map edges to any paths. Vertices, path of a median.
Okay, but you don't have the gates in MARIUSZ.
You don't have a gauge
Yeah,
path.
you use gauge invariance, but still, this isomorphism, I think, is maybe not gauge invariant.
No, but isomorphism is not gauge invariant. That's true.
So they're isomorphic like as algebras, but not as U1 algebra.
That's true. Yeah.
So
Okay. Yep.
what we're talking about is that you have three graphs.
Yeah.
And you have a relation between.
Yeah.
Okay. So it's
Yeah.
not a single straightforward map between these.
Well,
Okay.
just to have this isomorphism is a single straightforward map given by covariant induction, which we did not talk about.
Okay.
Or the isomorphism.
Yes,
So you have to reverse one.
But it has something more because, well, yeah, it's a pity that you didn't state this result earlier, because the name of the game is that the locally derived graphs are constructed in such a way that collapsing them is admissible graph homomorphism, which induces a gauge equivariant star homomorphism between graph sister algebras. But what does it mean? So you collapse it to the usual R graph, which means that now we have an embedding of a Kunz algebra O2 in M203, which is interesting.
Yes.
Yeah. This is how Jack got turned on. Because wait a second, so I can embed O2 in M203. And why is it funny? Because as everybody knows, you for certain congruence relations, you can embed OM in ON, but N is bigger than N. So somehow by amplifying it with matrices, we reverse the order.
Yeah, so let me maybe try to quickly go through another example.
But we have 40 seconds.
Maybe 40 seconds, that should be enough. So now I'm taking the graph that looks like this. So my graph L is a graph when I have a loop, when you have an edge, and then another loop. Okay, that's my E11.
So you should recognize as if you took quantum.
Exactly. And E12. Then I have V1, V2. Right, so that's the graph I'm starting with, and then that's my label. The labeling is here. So now, okay. First, I have to choose subgraphs, and now I'm choosing two subgraphs. So I'm
Disjoint.
two disjoint subgraphs. So I'm taking this guy and this guy.
Mm-hmm.
Right, that's my F1. That's my F2. Mm-hmm. And now the labeling, as we can see again, here I will label all the edges because every edge ends in one of the subgraphs.
Yeah.
So and that's the labeling. Where here A3 is the generator of Z3. Well, of course, I chose two subgraphs and now I have to choose two groups. And I'm saying for the first subgraph, I'm choosing the 3-element group Z3, second 3-element group, and then Z2 for this. So you can, if I label this by the generator, the loop here, I'm labeling by the generator of Z3, I'm labeling these two by the Z2, right? Because they end in this second sub. And if I do it like this, I'm getting, and here you see this unfolding. So that's your derived graph for Z. If you take just one loop and Z3 and you do this like, you get the derived graph like this, which already appeared in this block. If you take one loop and Z2, you get this derived graph. So you have two derived graphs here. But now here's this unfolding part that you have to remember. And this unfolding is important for the following reason. So first of all, it's a very nice graph. I don't know if you ever computed what C-star algebra of the graph was. I don't know. But it's an interesting question, what would be the C-star algebra? But what is important is unfolding. So the whole point of this derived graph is that I cannot just say, oh, I have two subgraphs, and then I do derived graphs. Because then if I try to collapse it again to this graph, right? Because our starting point were admissible maps. So now let me collapse it back to this. So the problem is that if I double those vertices, the range bijectivity tells me that I also have to double that areas.
Precisely. So that's the answer to whoever's question it was. Tomek, was it yours? No. No,
I was asking about this scaffolding.
But no, it was Lucas' question.
Yeah.
No, but Lucas asked what happens if we fail to unfold this one. So that's the answer.
Yes, that's what happens. Yeah. So finiteness, if I take finite groups, then there's no problem with properness. There's no problem with regularity if you do it like this. Well, no, there might be a problem with regularity. So we also want those subgraphs to be regular. So that will be another kind of thing. So
which means that if a vertex in a subgraph is regular in a graph, it must be regular.
Exactly. So regular subgraphs
cannot be a
exactly. So the construction of locally derived graph, we could take any groups, could be infinite, and we can also take any subgraphs. However, for this to make sense, for the main result that we were working on is this. If I now define the same projection, just the same projection on V, and if something was not doubled, it's identity. And then everywhere else is projection. So this is true if gamma i's are finite and if those inclusions are regular.
Yes.
So we need those two conditions. And then the proof that we had for the projection folding for derived graph is, well, this is much more involved because even checking that this is a homomorphism, remember this monstrous definition, right, with so many conditions in this bookkeeping. So even proving that this is a homomorphism,
it just requires verification.
But it's not difficult. I'm just saying that it's takes time and space in your paper. And then the proof of that result, if we assume those two things, so finiteness of groups and the regularity of the inclusions, it goes, I think, it's also, it uses the result we proved for derived graphs.
Yeah. It's generalization.
Yeah, so it's that's how this generalization looks like, and I guess that I should end the talk. I'm only gonna show you the result we had at the very end. Is that if you have an admissible subgraph in the graph, and if you assume that this projection folding from the locally derived graph now on F is admissible, then this diagram, and it happens to be it's a push-up diagram of in the category of graphs and graph homomorphisms. And then with Piotr, we were always interested in turning push-ups into pullbacks via this functor of taking stars here and reversing the arrows. So this surjective arrows, they are now injective ones here. And the question was, is it a pullback in the category? And there is some technical condition involving breaking vertices, as always. So for finite graphs, there's no additional condition for row finite graphs, but if you have breaking vertices, in general, there is some condition. And then under this condition, you can have a pullback coming from this natural push out of graphs where one of the arrows is clearly not injective. So that was the whole point of this, first of all, to find some new examples of admissible homomorphisms, but in such a way that, it's still interesting and it's related to the things that are already known. So that the derived graphs were very interesting examples. And then we ask ourselves, okay, so how can we generalize this such that still this admissibility can hold? And that's how we came up with this local derived graphs. And then we were able to prove this result for the pullbacks. And let me end with some questions. So the questions are as follows. So first, it would be nice to know some other known C-star algebras in topology or in general, whose are C-star algebras of locally derived graphs. So we have some examples, but we need more examples. So that's for sure. Because in the paper I mentioned, we were not interested only in locally derived graphs. In this talk, we were only interested in derived graphs. So if you find this interesting, you can try to find some new examples. So I'll be happy to talk about it. And then the question, is there a Gross-Tucker type theorem for locally derived graphs? Right? Because we know that if you have free action on a graph, then it has to be of a certain form of a derived graph. Here, should we talk about locally free actions of groupoids, or should we talk about partial actions maybe? Because parts of the graph are not touched by any action. Maybe partial actions. And then the follow-up question is there a Pungian pacified result for locally derived graphs? So there are cross products of partial actions, there are or locally free actions. And here, it would be interesting to know if it's possible or not. I have no feeling because I didn't try to prove this, but this is something that came up to me when I was preparing the talk. So I thought I'm going to leave you with some open questions to take home. So thank you for your attention.
Thank you so much. So now that the speaker has some questions to the audience, maybe now we can retaliate and ask the speaker some more questions. So anybody from the room? Just try to somehow have the mic not too hard.
Thank you.
But if you touch it, you switch it off.
Okay, so do you have any idea what would be the range of the K-theory in the case where you're not considering finite groups? Because with finite groups, you stay within graphs. Okay.
Yes.
Like some abelian groups, even.
So could you repeat? So what was the first question about?
So you also talked about derived graphs in the case where you don't have finite groups. Okay.
Oh, okay.
It's like Gibbs-Nevoid classical to me.
I mean, you can, of course, you can. I think that's how the K theory is proved, right?
Because you have cross product and
Yeah,
Yeah,
sure.
but
That's,
so the question, if I understand it, so take a C-star algebra of a locally derived graph. What is the range of possible K0 groups I can get?
or K1
Or K1.
even.
Yeah.
Yeah. So I mean, you could stay within a billion groups.
No, I
Modern, no idea.
That's an interesting question. I mean, I'm not.
Like, can you get? I'm interested in stuff like that, where you can recover like finely generated
So I can.
K theory, but you cannot get all groups through graphs because you don't have torsion in K1. So
Okay.
I mean, this is a very good question because you still have this Rebel-Szymanski formula. And you can apply Rebel-Szymanski formula to locally derived graph and see what it tells you.
yeah, but can you also see start seeing torsion?
Okay, I can tell you about a different result that I know of. Is that if you take any of them, the discrete, then you can. There's a paper by Goswami, Jodhar, where they define a graph such that K0 of this graph is this Abelian group they started. So there's a procedure.
Okay.
However, I don't think they keep track of K1 in this construction.
Yes. So yeah, the K1 is.
But I like your idea because surely the labeling of a voltage map, whatever you want to call it, will be involved in the formula giving you KT.
Yes.
And now you can try to do the reverse engineering. You want to have such and such a billion group as your K group, K1.
Yeah, so like
and
any
you solve for reaction.
Yeah, any finely generated a billion
Yeah.
that might have torsion. Can you see it through a K1 or such stuff? And through finite graphs? Finite groups? No, because you get graphs. But okay.
I mean, sorry, so to make sure, if you do our construction with infinite groups, you still get graphs.
Yes, you don't have star homomorphisms.
Yeah,
So there's graphs.
still you get graphs,
But it's graphs is the it's cross products.
but it's not.
That's
But this folding is not.
a star homomorphism. That's not induced star.
Does not induce a star homomorphism.
Okay, so you still get graphs.
Yes, but you still get graphs. So of course you can go to. You can try to do the same construction.
So
That's all.
like topological graphs.
Yeah, exactly.
Yeah.
So maybe for topological graph, that would be something. You can go beyond that, and this is also something I'm trying to do. I'm trying also to locally derived graphs, but in terms like treating derived graph as a trivial bundle. So now we have a locally trivial bundle, so your graph is a locally derived graph. So you have like two trivial bundles on the edge space and on the vertex space, and two bundles, and you try to think of reconstruction theorems and stuff like that for this. But it's a different way of having locally derived graphs. So this is a different. This is even kind of more interesting in the sense that in the realm when everything is discrete, we're still trying to have something locally, only locally trivial.
Anybody else?
if I can. So it was almost my question.
Also,
It's almost expired, but I have some version of it. So first of all, what are conditions under which all your constructions, local constructions, can induce star homomorphism between algebras, sister algebras?
what do you mean local constructions?
You have your construction,
Yeah.
especially this is locally derived.
So what we know
Right.
is this should be one of the slides. What we know is we know this, right? This projection fold. So this construction was done in such a way such that if groups are finite and inclusions are regular, you get a star homomorphism because this map is admissible. So the map the other way around from C star of E to C star of E alpha is you have a star homomorphism through this formula that we discussed at length.
Yes. So could this proposition be rephrased in something like, if some conditions are fulfilled locally, then globally something holds. Because assumptions are on this gammas, they are finite, about the inclusions are regular,
So the condition,
and
so
the
the conditions are local.
yeah, and the outcome is that pi is admissible.
Yeah, pi is global, right?
Yeah, yeah.
So I guess that's the conditions.
So
The regularity is the
Can, yeah, so can you say that if some admissibility holds locally, then globally it is admissible?
I mean, we have this result, I didn't mention this result, that if I have some admissible subgraph of my graph, then, and you take a voltage graph, and you build this locally derived graph for f.
Yes.
And so
This is a very important and not so obvious.
So if you build this one with the same labeling, you can build this graph, and then it will be a subgraph, but it's also an admissible subgraph. Right? So it's almost local. So you take some sort of, but you know, subgraphs for graphs here, you think it's very difficult to think about local open things. So it's more like a closed subgraph, right?
Yeah, yeah.
But it's a very good point.
Yeah.
So imagine that you have a graph which is an admissible subgraph of a bigger graph, okay? And then in this smaller graph, in the subgraph, you have this family of subgraphs and you do this locally derived construction. Then you can, of course, do the same locally derived construction in the bigger graphs, because a family of subgraphs in a subgraph will be a family of subgraphs in a graph. And then you can check that all these conditions will still be satisfied because of admissibility. But better still, what you can show is that this locally derived graph of a subgraph is now an admissible subgraph of a locally derived graph of a graph.
Yeah. Now the question is,
So can you merge these two propositions?
yeah, that was
So
the
it's a simple theorem.
Well, that we had this. We have this. What we just discussed is in here, and from this you get this. If you put it in a different. This is this push-up we started.
Yeah.
So the thing is that the question you might ask yourself is that why the same labeling? Because definitely there might be some more edges. And E, if you take this,
But admissibility takes care of it.
but yeah, admissibility takes care of the fact that you, so with the same labeling you can define this graph, and then you get admissibility. It's not surprising that this is a true result, but it's also not obvious.
So this is the direction of this proposition is from the global to local.
No, from local, because you start with something that is
this subgraph.
subgraph. So you start with a subgraph, and then you prove something for. Then if you do this,
So you starting from something global, you are checking some condition locally.
No, you have both. I wouldn't say that it's from two. You have, on one hand side, you are local, on the other side, you are global, and you are combining the two. I mean, F is an admissible subgraph of E, so this is global, if you want. Alpha is this locality issue. And then we say that if we have F alpha, then it's also an admissible subgraph. And but still under some further conditions, we have a very nice exemplification of our general pullback theorem, which is precisely in the situation when one guy has to be injective, so one star homomorphism surjective, but the other one we want to be non-surjective on the star homomorphism, or if you want at the level of graphs, you don't want to be injective. And we needed some nice examples, and these locally derived graphs gave us such examples. Of course, we could do the same with derived graphs, but a reason why this idea came up is that somehow I was looking at examples of derived graphs, it looked a little bit like Morita equivalence, it looked a little bit like tensoring the matrices. I didn't like it. So I wanted to have something more fancy. So I said, okay, let's look at this SUQ2 graph, right? And then let's blow one circle by Z3 and another by Z2. Okay, so one circle will be tensoring 4x4 matrices, another will be tensoring with 3x3 matrices. So there is no Morita invariant. It's something more general. This was how these derived graphs were born.
Yeah.
I wanted to have more fancy examples of,
So this example with
more interesting sister algebra, not just tensoring by matrices.
yeah. So this example is DTP. That's I should have mentioned that also. This very nice example that shows you, because if you do the derived graph, you start
Just tensoring the matrices.
Yes, you start with a loop. Let me maybe write that. So you start with a loop, which is just graph sister algebra of this are just function on the circle.
Yeah.
Right? And then your derived graph with the labeling we just did here, right? So it would be, so this graph, if you have 1, 2, 3,
These are 4x4 matrices over Brazil.
4, 3, right?
If you have
It's
3
all
edges,
correct, yeah,
it's 4. One edge means 2x2. So.
Yep. Okay. Over this one. So we're just tensoring with matrices. That's good. So just you look at matrices with values in this algebra. But now, if you have a different matrix algebra here and different matrix algebra here, then all of a sudden it's not. Even in this very simple example, it's not just Morita equivalent to this algebra. It's something else. It's locally Morita equivalent.
Can you glue these local pieces into some?
Well, let me. Okay, so my answer is. You see, we assumed here that these subgraphs are pairwise disjoint, because already here the definition was quite complicated, and it was good enough for our purposes of having, examples. But somehow we believe that you can remove this assumption, but you really would have to do some good care about the intersection. For instance, if you have two different groups that you intersect, so where do you map it? Maybe to back a different product of the group. I don't know. But somehow for me, what would be interesting is to generalize this locally derived construction to the case when you no longer assume that your subgraphs are pairwise disjoint, and maybe you have a groupoid which is not just such a primitive groupoid which is a bundle.
Yeah, so maybe just last comment because some of you was asking about many things. So maybe this name locally is not what it means in topology.
Yeah, because that comes with a cover.
Exactly, because here everything is discrete. So there was no chance of having something. If you go to topological graphs, then you can do what you're asking. So you can think, okay, so let's take some open subgraphs. I suppose I got my, and then from open data, you glue it in such a way you have some, so only locally it's trivial, and then from local data, you build the whole thing. But here, it's just, discrete graphs, and there's no hope for that. But still, by taking many groups, and by taking different disjoint subgraphs, we were able to have something that locally looks like a derived graph, but it's not a derived.
I was not thinking about these topological graphs. What I had in mind is that, of course, tensoring with matrices is a Morita equivalence. But you can have Morita equivalences more complicated than that. Sure. They can come from finitely generated projective modules. Sure. And my question was rather about combining this local data into some finitely generated projective module. And then it could lead even to something like Morita equivalence. Sometimes, maybe. I don't know.
No, it's a very good point. I like your question.
Yeah, that's true.
I like the question, but we don't know the answer.
Yeah, exactly. Even in this example. We only know it's not only those multiplied and tensoring by matrices. We don't know. Maybe this is some sort of more.
Yeah. And there's a reason why I'm interested in that, because when we go to K-theory, then global Morita equivalence vanishes. Okay? So my question would be, in this situation, can you avoid this local tensoring with matrices, okay, to disappear in K-theory, for instance?
One should compute Lagrange lines.
So this is
we just
compute.
Just somehow
It's computable.
Yeah.
yeah.
You see, our motivation was, when you go back to the slide with the pullback theorem, our motivation was because this is what the referee demanded. The referee demanded, okay, give us more examples of your pullback theorem. And we said, okay, since our pullback theorem, the name of the game is the essence of the novelty of our pullback theorem is that it applies no longer to just injective maps between graphs, okay? So all that we need is that these are admissible star homomorphisms, okay? But they can easily be non-injective, like these projection foldings. So the referee demanded examples, so we came up with this class of examples here, which was completely new. And that's it. This was our motivation, and this is what we looked at, and we proved that pullback theorem here. But you can have many other questions. I'm just explaining why we did it.
Yeah, so that's the reason for this talk, right? So, because there are many questions about those local derived graphs that we didn't have time to answer.
Yeah. But this is why I believe it warranted a separate talk, because we already had talks about the pullback theorem and contravariant factoriality, right? But this deserves, it's like a separate chapter in itself.
So it reminds me another story from topology or from algebraic geometry, when instead of speaking about classical topology, you can speak about more general Gaussian topologies, where analogy of an open embedding is changed to partial, for instance, coverage of open subsets.
Mm-hmm.
So they are partially surjective even maps.
Yeah.
Okay. So these are called étale maps. Okay. So this is such a situation when you are replacing something injective by something which is partially even surjective.
Yeah. I agree.
So this is an analog of some
The
more general
yeah.
Gaussian topology, comparing with the classical topology.
Yeah.
Usual spaces.
True that, yes. Yes. And another reason why we like this locally derived story is that it led us to these embeddings of Kunz algebras in matrices over Kunz algebras, or more generally matrices over Kunz into matrices over Kunz. And there is it's another story. This is my work with Yang Liu.
You can correct me here, but it was also a stumbling block because you wanted the map.
Yeah, it was also a stumbling block because at the beginning, because I came to Trieste from Arizona. So when I was chatting with Yang and first idea was that we would like to get. Okay, because let me start from the beginning. There is this beautiful theorem that tells you that for a certain type of algebras, I mean simple, unital, nuclear, very good, nice algebras, okay? If K-theory allows a unital star homomorphism, then it exists. So basically, you just look at a billion groups, which are K groups, and then but it has to be preserved unit, right? And then you can see that if you want to map one Kunz algebra to the other Kunz algebra, well, this has to induce a homomorphism of K0 groups, which are torsion groups. And the generator of the torsion is the class of 1 in your algebra. So one generator of the torsion has to go to another generator of the torsion, which enforces a congruence relation for this to make sense. But if this congruence relation is satisfied, you know that such a star homomorphism exists. And then I forgot what was the name of Kawamura. He wrote an explicit formula. So you can have all these embeddings of OM in ON, where M and N satisfy a congruence relation. But they have to satisfy a congruence relation. It's not like you always have it. Okay. And this is why with Yang we wanted to say, okay, so now we know congruence relations when we deal with matrices, because we immediately, we have O2 in M203. So how about having something more general? Okay, just let's look at the congruence relation, which is immediate, and then see if we can construct such a star homomorphism when this congruence relation is satisfied. And at the beginning we said, okay, so we should get it by this locally derived graph, as it happened in this special case. But very quickly it turned out that the only generalization we can obtain this way, you see here we have an embedding of O2 in M2O3. So in general we can embed ON in MN ON plus 1. That's how far away we could get with locally derived graphs. But it completely failed for more general situations. And I said, screw locally derived graphs, let's do something more general. And then we found the formula.
Yeah, so the moral of the story is that locally derived graphs are great, but they're not good for everything.
Okay. Okay, anybody else? Anybody from the Zoom who survived? Ali, you want to ask a question?
Yes, excuse me, I have a question. Can I ask?
Sure, go ahead.
Yes, you refer, first I would like to thank you for this very great talk. I have to watch this video again to understand the detail, but I have a few questions. In particular, you refer to a theorem by Hayek, by Piotr, that if we have an admissible morphism between two graphs, then you define a very interesting contravariant factor in the corresponding C-star algebra.
It's our joint theorem.
Sorry?
It's our joint theorem.
Yes, yes. My question, maybe my question is elementary, but is it obvious, is it straightforward to check that this is really a well-known morphism, or there is no any technical difficulty to prove that this is really well-known, well-defined morphism?
I mean, so the proof, the whole idea was to come up with the good notion of admissible graph homomorphism, right? So we wanted these two formulas. Sorry. So we wanted these two formulas, these assignments to give you a star homomorphism. Then the question is, okay, and then another restriction was that we wanted to start with a graph homomorphism, because this was true for subgraphs. So we wanted to generalize the case of subgraphs. Those subgraphs are sometimes called quotient graphs in the literature. And they are not quotient constructions in the graph. But on the C-star algebra level, they're quotients. So the question was, given a graph homomorphism and this formulas, what are the conditions on the homomorphism? So what's this admissibility so that you get? And then if you just trying to prove that what would this mean, it gave us those two very natural conditions. So the regularity conditions comes from, regularity and the two, and then I think this range bijectivity was the most kind of surprising and unexpected. So if you look at this should be kind of, we thought maybe it will be easier because it's this S star S equal P is this kind of easier of the relations from this conscriptive relations, right? This is the one that is really making them interesting, those algebras. Without this formula, you get bigger algebras. You get the algebras that are called Teplitz algebras. And already for Teplitz algebras, Teplitz graph algebras, this range bijectivity is an interesting condition. So I mean, when you have the right conditions, then the proof is just you do the calculations and they agree because if you choose the right conditions, that's the whole idea. The difficulty was to find the conditions. For sure.
That's true, but even the very verification, it takes several pages.
Sure.
I mean, it's straightforward. I mean, Mariusz is right. It was reverse engineering to find these conditions, and then you check whether everything works. I mean, it's completely straightforward, but it's lengthy. It's not immediate.
Yes, okay, thank you. As another question, you started your talk with the concept of the voltage on graph. It is an arbitrary map from the set of weights to the groups. I was thinking about the following. Assume that let's consider the special Cayley graph of a group G. So for a given group G, we have a Cayley graph, and there is an obvious voltage which can be defined on the Cayley graph of the group. In the literature, are there some research devoting to this kind of derived graph or no?
Yes, so exactly. So that's a very good question. I happen to know the answer, so I'm also happy with that. That if you take the Cayley graph, right, then the group acts freely on the Cayley graph. So you know that, let's say, finely generated group form. Then you know that it is a...
Yes, we assume that the generator is a finite set, yes.
It will be a derived graph, right? So the Cayley graph is the derived graph, and the question is, so what's the voltage graph? So the voltage graph is the Kunz graph. So you take just one vertex, and every loop is the generator, right? And then the voltage is to each loop give one generator of the group, and that's how we get the Cayley graph as a derived graph. So you can always get the Cayley graph as a derived graph.
And whose result is this?
This is again Gross and Tucker.
Okay.
So it's in this book. So
Yeah.
maybe it's still there, somewhere there. I don't know. It's in this book, Topological Graph Theory by Gross and Tucker. Yeah, let's see. So you can find this result in here. So they discuss Cayley graphs. And then, so they discuss Cayley graphs here as well. But that's a very natural question.
Yes, thank you.
Okay, anybody else? Adam, are you happy?
Yes, I'm still here and I'm happy. Thank you.
Okay, so I think our ramen is getting cold, so let us thank Mariusz again.